Flood disasters occur annually within the United States and around the world, contributing to widespread property damage, threatening critical infrastructures, and causing the loss of food productivity. During a flood disaster, a critical information the first responders need to know is where the flood water is located. Collecting such information on the ground is both unsafe and inefficient. Fortunately, the increasingly available remote sensing data from the airborne and space platforms provide a unique opportunity to map flood extent on a large scale. The key question then is how we can develop effective and efficient data science algorithms that can automatically classify the remote sensing data into flood extent map. However, this is non-trivial due to several technical challenges. On the left is the sample imagery collected by NOAA National Geodetic Survey during Hurricane Mathew in 2016. And there are several challenges here. First, the data volume is large. There are billions of pixels in only one city for high-resolution imagery. Second, there are rich noise and shadows in the image. Third, floodwater locations follow implicit topographic constraints. Due to gravity, water flows from high locations to nearby lower locations. Finally, there are obstructed views such as tree canopies, clouds in the imagery, making it hard to identify floodwater beneath. Here is a zoom-in view. There are tree canopies overlaying floodwater. To address these challenges, we propose a novel probabilistic graphical model called the Geographical hidden Markov tree. Here is one illustrative example. The horizontal axis shows locations in one-dimensional space, and the vertical axis shows elevation values. There are 8 spatially contiguous pixels or locations in the example, from 1 to 8. Due to gravity, if location 5 is flooded, then locations 2 to 4, 6 to 7 must also be flooded, even if their imagery features indicate otherwise, such as tree canopies, which could have been the dry class. We represent such dependency as a partial order constraint in a reverse tree structure. In the reverse tree, if any node, such as node 5, is flat, then all the subtree nodes must also be flat. The reverse tree structure is put into a hidden class layer, and each hidden class node is also associated with an observation feature node. In this way, a pixel's class is determined by not only its own spectral features, but also nearby pixels' classes following the partial order constraint. Here are some results from a case study in Hurricane Mathew. The top 2 figures shows area imagery and digital elevation information. The lower left shows the result of random forest classification. And the red color shows the predicted flood locations. It can be seen that random forests only identify the exposed water surface. In contrast, our hidden Markov tree model identifies complete flood extent due to the incorporation of topography. For more details about our models and algorithms, please come to our presentation.